In today's session, we will discuss about the multi-objective optimization. So, actually, the optimization is actually what we have to find out one or more feasible solutions which corresponds to extreme values of one or more objectives. That is, so there are some objectives. We have some objective functions or objectives that is to be maximized or it is to be minimized. That is, we have to find out the extreme values of these objectives. And the optimization refers to finding out these, finding out the parameter values of the parameters. That is, the feasible solutions. The values of the parameters. A set of feasible solutions is a set of what you say values of parameters, a set of values for the given parameters of the given problem. So in optimization, what we are actually does is we find out a feasible solution. It can be one or more than one feasible solution is also possible in certain cases. And we want to find out this one or more feasible solutions which corresponds to these extremes. That is either the maximization or the minimization, depending on the type of the objective that is at hand. Suppose in the case of profit, if our objective is the profit, then it is to be maximized. If it is the cost, then it is to be minimized. So that is how the optimization works. An example of an optimization problem is given below. That is minimize f of x. Normally, this is how the objective is written. That is minimize then f of x. This is a single objective. We are giving only a single objective here because only one objective is there. Then subjected to some constraints. The constraints normally it is written in the case as less than or equal to 0, as well as equal to 0 conditions. There are two different conditions that is possible. One is less than or equal to 0, as well as equal to 0. And obviously there is a possibility that greater than or equal to 0 is also possible, but we are avoiding that sort of constraints in this case. So two different types of constraints are involved: g, j, x less than or equal to 0. So for j equal to 1 to nj, so there will be n different j values in this case. And hk x equal to 0, so k equal to 1 to nk. So k different, I mean n different hk values are also there. So then xil should be less than or equal to xi less than or equal to xiu. That is, all the xi values, all the values corresponding to the x can be a vector. That is a vector corresponding with a number of variables in that case. So that is the minimization function. This minimization function can be a function of different variables, but all the different variables are together denoted as x. So the x can be an array of different variables, and each x values, that is each element in the x array should be within a lower limit and upper limit. So that is this condition. So this is the general terminology or general method of expressing an optimization problem. Now, till now what we have discussed is the optimization as well as search problems having only a single criterion. In all your course project examples also, there was only a single objective was there, or a single criterion was there. The criterion can be either maximization or it can be minimization, but there was only a criterion. And then this particular criterion is transformed to a fitness function. That is, a function is generated based on this particular criterion, or the criterion itself becomes the fitness function. In some cases, the criterion itself becomes the fitness function. Otherwise, we have to transform the single criterion into a fitness function, and then we proceed with the reproductive as well as genetic operators, the different types of reproductive plants as well as the genetic operators we employ in order to find out the solution corresponding to an extreme value for this particular criterion. Whether that can be the minimum extreme, or it can be the maximum extreme. So this approach of considering only a single criterion for the optimization problems is good for many problems. It is okay for many problems, but there are some problems, some type of problems in which several criteria are present, in which there are multiple criteria are present. That is, we have to minimize something as well as maximize something, and all these criteria come simultaneously also. It is something like purchasing a car. When you are want to purchase a car, uh, you obviously want to minimize the cost as well as maximize the comfort. So that is the condition in while that is the two criteria that are to be taken care of while purchasing a car. That is, you have to minimize the amount involved, the cost involved, and you have to maximize the comfort that is attainable from that particular car. So these two criteria are simultaneously present, and when we want to go for solving this type of problems, it is known as multi-objective optimization problems, because more than one optimization criteria are present there. And in some cases, these criterion or these objectives cannot be combined together into a single number. Like in our case, we cannot convert the prices in the terms of rupees or dollars, but the comfort cannot be converted in terms of rupees or dollars. That is, in terms of monetary terms, you cannot express the comfort. So that is the difficulty. If you could express the comfort also in terms of monetary terms, then obviously you will be able to, what you said, convert both these objectives into a single objective. Then you can apply your normal optimization procedure to optimize for that particular criterion. That is a single criterion method in that case. So when multiple criterions, that is more than one criterion, are involved in the optimization problem, that type of problem is known as the objective problem, multi-objective optimization problem, or also known as the multi-criteria optimization problem. That is, since there are more than one criteria is involved. So the multi-objective optimization problem started all in the early 1960s. Till then, the multi-objective optimization problems was not much explored, but in the 1960s, the multi-objective optimization problems have received an interest from the researchers, and thus the researchers started to explore the possibilities of multi-objective optimization problems. So as we said earlier, in a multi-objective optimization problem, multiple objective functions need to be optimized simultaneously. So in many cases of the multiple objective or multi-objective optimization problem, or in all the cases of the multi-objective optimization problems, there does not exist a single solution that is best with respect to all the objectives. This is because of the differentiation between the objectives. So in some cases, the objective may be minimizing in order to minimize and minimize a certain quantity, like minimize the cost involved. And on the other hand, it may be the maximization of comfort, etc. So that sort of cases, if we find a car or we find a solution with a minimum cost, then the comfort it offers may be not that much. The comfort will be less in that case. That is, if we minimize the cost, then the comfort will be less. And if we maximize the comfort, then the cost will be higher. So that is a conflicting situation. So what we have to find out in that cases is we have to find out different solutions in terms of these two different criteria, these two objectives, and then you have to select one alternative from all those things. which is a compromise between different criteria. So that is the solution. That is the solution for the multi-objective optimization. It is first you have to generate a number of solutions, then select a specific solution from that one, depending on some compromise between these solutions. So, and while selecting this particular solution also, there is a possibility that it may be best in one objective and worst in another case. So that is that is a possibility in the case of multi-objective optimization. That is, if you select a particular solution which is best in one in a certain objective, then it may be worst in another objective. If there are multiple objectives, it may be worst in all the other objectives also. That is also possible. So what we have to do in such cases is we have to select a number of solutions or a set of solutions of multiple objectives. Then these cannot be compared with each other. These cannot be compared with each other without giving some sort of what you say compromises, without using some sort of compromises. We cannot compare both of them. So for such solutions, these type of solutions are called as Pareto optimal solutions, or also known as non-dominated solutions. That is the solutions that is selected for a multi-objective optimization problem in which case none of the solutions cannot be compared directly with the other without some compromise. So in these cases, no improvement is possible in any objective function without sacrificing at least one of the other objective functions. That is the condition. So in Pareto optimal solutions, the solutions known as the Pareto optimal solution or also known as non-dominated solutions. In those type of solutions, that is the non-dominated solutions or the Pareto optimal solutions, no improvement is possible in one of the objective functions. That is one of the if you are comparing two different solutions and one is better, and if there are two different objectives, one solution will be better in one objective and the other solution will be better in the other objective. So that should be the condition. So in that case, so you can consider both these solutions as Pareto optimal solutions, because if you improve or if you select the solution with the better objective function for the first case, then in the second case, the second objective function may be having a lesser fitness value. So that sort of that is the condition with the Pareto optimal solution. So using this concept of Pareto optimality, we find a set of solutions that are all optimal compromises between the conflicting objectives. So that is what we do. We find a set of Pareto optimal solutions, and this Pareto optimal solutions are actually the optimal compromises between the different conflicting objectives. So this Pareto optimality is actually a concept used in economics and game theory, etc. So, but it is being but used also in the case of optimization problems also. So then there is there are two different terms in which are related to the Pareto optimality conditions. That is the Pareto optimal solutions that we have already talked about or discussed about. That is the optimal solutions found in a multiple objective optimization problem. That is the Pareto optimal solutions. The optimal solutions in terms of the objective functions. The increment in one objective function should lead to a decrement in the other objective function. So that is the Pareto optimal solutions. Then the Pareto optimal front. The Pareto optimal front is the curve formed by joining all these solutions. That is the curve formed by joining all these Pareto optimal solutions in case of an objective function space. That is the objective function will be denoted in the x-axis as well as y-axis and z-axis if possible, if there is an z-axis. Then in all these axes we represent the values of the objectives. Suppose if there are only two objectives, we have only two objectives and one objective. O1 is represented in the x-axis and O2 is represented in the y-axis. So then this is the objective space. That is, the objective values are represented here. So there is a particular solution. The objective values of the solutions can be represented here. There is a particular solution where this is the corresponding value of O1 as well as this is the corresponding value of O2. So then there is another solution here. The value of O1 is here and the value of O2 is here. So like this, all these solutions are marked, and then the boundary of the curve. The boundary of the curve is gives you the Pareto optimal solutions, and the curve formed by joining all these Pareto optimal solutions is the Pareto optimal front. Then non-dominated as well as dominated solutions. And non-dominated condition is suppose we are given two objectives. There are only two objectives in our case. We consider only two objectives. So a non-dominated solution is when none of both solutions are better than the other with respect to two objectives. That is, both objectives are equally important, like speed and price. So in that case, none of the solution is better than the other in both the cases with respect to the both objectives. So in one objective, one is better, and in the other objective, the other one is better. So that is a condition. Then a dominated solution is a solution. Suppose we have a solution A, which is no worse than B in all objectives. That is, and a solution A is strictly better than B in at least one objective. Then solution A dominates solution B. That is, we have two different solutions, and we have multiple objectives are there. Suppose we have 3 or 4 multiple objectives are there, and A is no worse than B in all objectives. That is the fitness of all the objective functions of A, all the objective functions of A, the fitness values corresponding to all the objective functions of A is at least as good as that of the B. That is the fitness of the objective functions of B is at least as good as the fitness functions of or fitness values of B. And in at least in one case, and at least in one objective case, A is better than B. So if there are, say, 5 objective functions, O1, O2, O3, O4, and O5 are there. So in these cases, suppose we have O11, that is the O1A. Okay, O1A equal to O1B and O2A equal to O2B. This is the objective function value of the first objective function corresponding to the solution A, and this is the objective function value corresponding to the first objective and corresponding to the solution B, and O2A and O2B is the corresponding objective functions for the second objective. Then O3A is better than O3B. So the and O4A equal to O4B, O5A equal to O5B. So in all these cases, in all the 5 cases, the objective function of A, is at least equal to the objective function of B, and in one case, the objective function of A is better than the objective function of B. So this is a situation where the solution A is said to be dominate. A dominates B, or also known as B is dominated by A. So B is dominated by A, or A dominates B. And then there is a concept of weakly dominated solutions. Weakly dominated solutions is nothing but when a solution is no worse than B in all objectives. Instead of this case, if it is O3A equal to O3B, so in this case, all the solutions, all the objective functions are having the equal values. So in this type of solutions are known as the weakly dominated solutions. So the concept of domination is the solution x1 is said to dominate the other solution x2 if both conditions 1 and 2 are true. The conditions 1 and 2 are true. The solution x1 is no worse than x2 in all objectives that we have already said. The solution x1 is strictly better than x2 in at least one objective. That we have discussed. That is the concept of domination is already discussed. Then the multi-objective problems dominance, we say x dominates y if it is at least as good on all criteria and better on at least one. So like suppose we have a solution x here and we have a solution y here. So in this case y is suppose this is a maximization problem. This is max and here also it is max. So maximization of f2 means it should be towards the right end, and maximization of f1 means it should be towards the top end. So a solution like this is maximum in the case of f2, but it is minimum in the case of f1. And here is a solution. This is a somewhat maximum in the case of what you say, the f2, and somewhat better than the previous solution in the case of f1. So these sort of things, or this set of solution. So this solution is this set of solutions generates a Pareto front, because in this case, if you consider this solution as well as this solution is better in the case of f2, but it is weaker in the case of f1. This solution is better than this solution in the case of f1, and weaker in the case of f2, corresponding to this solution. And corresponding to this solution, if you consider this solution is better in the case of f2 and weaker in the case of f1. So that is the condition. If you consider any two solution in this particular curve, that is shown, one solution will be better in one function and the other will be better in the other case, and the other function. So if we consider a solution somewhere here, then x is better both in terms of f2 as well as f1 in this case. If we consider a solution here, and if we consider x as this one, this is y, and this solution x is better than the solution y in both the cases, both the objective functions. In the case of f2, x is better. In the case of f1, x is better. And if we consider this solution, suppose if we consider this solution, say this solution is z, and if we consider y and z, what will happen? This y is better than z in the case of f1, but it is worse in the case of f2. So that is, and so this solution dominates all the other solutions, and all the solutions in this range or in this particular curve dominates all other solutions. So all the solutions that is falling within this area, within this particular area, is dominated by x. All the solutions falling within this area is dominated by x, and all the solutions that is falling within this area, say within this particular area, this is dominated by z. So all the solutions falling within this area is dominated by z, this particular solution. That is the concept of Pareto front. And the solutions that is falling on this particular region, on this particular curve, is not dominated by any other solutions. So this is a case of maximization as well as a minimization condition. So this is a minimization, f2 is a minimization and f1 is a maximization. So maximization means it has to be towards the right end, and minimization means it should be towards the bottom end. So this means this two line, these two particular solutions, These form a level 1 solution. Level 1, or it will be in the Pareto front, because this solution, this particular solution is better than this solution in both the cases. This is it is maximum more, or it is larger. 3 is larger than 1 in the case of F1, and 3 is smaller than 1 in the case of F2. So this is dominating. This particular solution 3 dominates the solution 1, and the solution 5 also dominates the solution 1, because it is equal in the case of F2, and in the case of F1, 5 is better. So this is a level 1. And here, if we draw a line here, this can be a level 2, because if this particular set of solutions were not there, if this particular set of solutions were not there, then this set of solutions, this 1 and 4, will be forming the Pareto front. So that is the case with the dominance. So some Pareto optimality examples. Normally, if you are considering only two objective functions, there will be 4 different conditions that will be arising. That is, one is both the conditions are minimization, both the objective functions are minimization, and the other condition is one is minimization and the second one is maximization. The first one is minimization and the second one is maximization. And this next condition is the first one is maximization and the third one is minimization, and the last one is both are maximization. So if both are minimization, the Pareto front will be here, the dark line, the dark curve that is representing. That is the min-min condition, the min-min Pareto optimal condition. And in the case of min-max condition, it will be this curve as well as this curve, these two curves. These two curves will form the min-max Pareto optimal front, and the max-min Pareto optimal front will be here. Max-min Pareto optimal front will be here, and the max-max Pareto optimal front will be here. So this is the different Pareto optimal conditions in the case of two objective functions. So then obviously there are some non-Pareto classification techniques also for the multi-objective conditions. The main non-Pareto classification technique is converting all the objectives into a single objective function by giving some weights. So there are some difficulty involved in this case, as in the case of the car. As I said, the price as well as the comfort, both these terms cannot be converted into the same term. You can add two terms together if both are in the same units. Otherwise, comfort cannot be added to the price. So that sort of problems are coming up. So there is, if we have multiple objectives, then we take a weighted sum of the multiple objectives together. This is something like a Pareto optimal solution, but with the different parameter settings, you have to run this run the algorithm multiple times, or run this particular problem multiple times in order to obtain multiple solutions. So that is a concept, that is a method of non-Pareto classification technique, that is aggregating the objectives into a single and parameterized objective function and performing several runs. And another method is the vector evaluated genetic algorithm. It was proposed by Schaffer in the mid-1980s, that is in the 84 and 85, two papers were presented. And in this case, only the selection mechanism of the GA is modified. In this vector evaluated genetic algorithm, the selection mechanism of the genetic algorithm is modified. During each generation, what happens is a number of subpopulations was generated by performing proportional selection according to each objective function intent. Suppose we have 3 objective functions, and if the population size, the entire population size is then equally divided into 3. If there are 100 is the population size, and if there are only 3 criterions, then we divide it into 3 different populations, so 33, 33 and 34. So that is the 3 subpopulations, and each subpopulation is generated based on based on each of these particular objective function. That is, objective function 1 is used to select the subpopulation 1, and the subpopulation 2 is selected based on the objective function 2. Subpopulation 3 is selected based on the objective function 3. So in this case, while selecting a specific subpopulation, all other objective functions are not considered for sorting or for doing the operations inside the GA. So that is the vector evaluated genetic algorithm. So thus, for a problem with the k objectives and a population size of m, k subpopulations of size m by k each would be generated. And these subpopulations are then shuffled together to obtain a new population of size m, on which the GA would apply the crossover and the mutation operators in the usual. So that is the condition. We generate number of subpopulations, and the number is dependent on the number of different objective functions. And then all these subpopulations are merged together or shuffled together, and then the usual crossover and mutation operators are employed. And this is a schematic of the VEGA selection, that is the vector evaluated genetic algorithm selection. So here is the particular generation, and in the step 1 we divide all the parents into n different subgroups, and then it is shuffled together, or n different subgroups are generated or selected from this population, from the original population, based on each of the objective functions, and then they are merged together, and then the genetic operators are done for the next generation. And the advantages and disadvantages of VEGA. So it is efficient as well as easy to implement. The VEGA, the vector evaluated genetic algorithm, is efficient and it is easy to implement. If proportional selection is used, then the shuffling and merging of all the subpopulations corresponds to averaging the fitness components associated with each of the objectives. That is, if we use the proportional selection in the case of if a particular objective function is having a higher priority, then more number of solutions are selected based on that particular objective function. So that is the proportional selection. In that case, then we merging this shuffling and merging these subpopulations corresponds to averaging the fitness components. The fitness components are averaged in that case. So that is possible. So in other words, under these conditions, VEGA behaves as an aggregating approach, and therefore it is subjected to the same problems of such techniques. So that is the difficulty. So if we employ the proportional selection only, in that case this VEGA, that is the vector evaluated genetic algorithm, behaves like an aggregating approach that we discussed before, and it also, this VEGA also will be having the same problem as that of the aggregating techniques. So now we discuss the problems in multi-objective optimization. So like a weighting method example, if we consider an aggregating method, this is weighting method is a method of converting multiple objectives into a single objective. And in that case, if the fitness function is something like this, W1 F1x plus W2 F2x, and W1 and W2 are the weights given to each of the objective functions, and objective functions are F1x is the response time and F2x is the throughput. That is how much quantities are generated. So then the problem with this one is the response time is to be minimized. We have to minimize the response time and we have to maximize the throughput. The problem with this type of representation is that it is hard to find the values of W1 and W2. How we will find out the values of the weights? So that is difficult. That is, if we give more importance to response time, then the weight of that particular one should be higher. And if we give more importance to the throughput, in that case the weight of W2 should be higher. So that is so it is mostly difficult to find the values of W1 and W2. And again, it is hard to form a fitness function because one is the minimization and the other one is a maximization condition. So developing a fitness function based on one minimization and the other maximization is difficult. If both are maximization, obviously we can do it by adding it together. And if both are minimization, then also we can do it by adding it together, no problem. But if one is minimization and the other one is maximization, then creating a single objective function or single fitness function is difficult. Then there is another method of non-Pareto optimal conditions, that is the lexicographic ordering. In this method, the user is asked to rank the objectives in the order of importance. That is the condition. Each objective is ranked according to its importance. So the optimal solution is then obtained by minimizing the objective functions, starting with the most important one and proceeding according to the assigned order of importance. That is, we first minimize or maximize depending on the condition, minimizing or the maximizing the first objective function or the objective function with the maximum importance. Then the next one, the next important one is minimized or maximized or optimized. So that this is done until as the solution is converged. So then it is also possible to select randomly a single objective to optimize at each run of a GA. That is also possible in the case of lexicographic ordering. That is on each generation of GA, one particular objective function is optimized and all others are left as blank. So that is also possible. So then there is multi-objective evolutionary algorithm. An MOEA, that is a multi-objective evolutionary algorithm, has additional operations to maintain multiple Pareto optimal solutions in the population. That is, other than the normal optimization operations that is to be done in the population of the the evolutionary algorithm, in order to find out the Pareto optimal solutions, some other additional operations are also to be involved. Then the advantages of MOEA is it deals simultaneously with a set of possible solutions. It enables of finding several members of the Pareto optimal set in a single run of the algorithm. That is, multiple solutions. Both says the same thing. That is, the multiple solutions can be found out in a single run of the algorithm itself. But in the case of this Pareto optimal methods, in that case, only one solution will be obtained in a single run. Then explore solutions over the entire search space. The entire search space is selected for exploring the different solutions. Then less acceptable to the shape or continuity of the Pareto front. As we have seen in the previous case, some conditions will be having a Pareto optimal condition like this. So that is, here there will be a breakage. So this is this won't affect the effectiveness of the MOEAs. Then the disadvantages is it is not completely supported theoretically. No theoretical explanations are available for the working of this multi-objective evolutionary algorithm. And there is a multi-objective genetic algorithm, MOGA. It is proposed by Fonseca and Fleming in 1993. And this approach consists of a scheme in which the rank of a certain individual corresponds to the number of individuals in the current population by which it is dominated. So the rank of a particular individual depends on the number of individuals it is dominating. That is, this suppose we have a certain number of solutions, 1, 2, 3, 4, 5, up to 10. If we have 10 solutions, then the rank of this first solution will depend on how much solutions or how many solutions is under this particular solution, or how many solutions is dominated by this particular solution, how many solutions are dominated by this particular solution. So depending on that condition, we are finding out the rank. Then it uses fitness sharing and mating restrictions. So then there are other ways of multi-objective genetic algorithms also. And the advantages and disadvantages of MOGA, that is multi-objective genetic algorithm. It is efficient and relatively easy to implement. Its performance depends on the appropriate selection of the sharing factor. So that is it. The MOGA has been very popular and it tends to perform well when compared to other evolutionary multi-objective optimization approaches. And then there is a non-dominated sorting genetic algorithm also. This is another part, another way of implementing this Pareto optimal solution. It was proposed by Srinivas and Deb in 1994. Then it is based on the several layers of classification of the individuals. As I said in the case of the example of dominance, there are several layers of classification or several levels of classification in this case. And the non-dominated individuals get a certain dummy fitness value and then are removed from the population. So the most apt solution or the most optimized solutions, the most non-dominated solutions in the outer layer, they will get a certain fitness dummy fitness values and then are removed from the population. The process is repeated until the entire population has been classified. That is, the entire solution, the entire population is classified into different layers, and on each layer, if all the other layers prior to this particular layer is not present, in that case this particular layer becomes the Pareto optimal front. So then to maintain the diversity of the population, the classified individuals are shared with their dummy fitness values. So that is in order to keep the diversity of the population. If we are keeping only the Pareto optimal solutions only, in that case the diversity of the population is lost. So what we do is we classify the individuals into different classes, and then in order to keep the diversity from each classes, the individuals are shared or selected. And that's all with the multi-objective optimization. Thank you.